The Big Bang, 13.8 billion years ago.
We, CERN, are trying to understand matter.
We built a world-class physics laboratory with the most powerful particle accelerators.
Fundamental research in particle physics not only pushes back the boundaries of our knowledge of the universe,
but also catalyzes innovative technology developments. We built a bigger machine, the LHC, with bigger detectors.
Alice,
Atlas,
CMS,
LHCb. The scale and demands of our accelerators, detectors, and computing infrastructure
constantly push the boundaries of technology.
Together with our member states, associate member states, and partners across the globe,
We develop state-of-the-art technologies in different domains.
Technology that impacts and saves lives.
When the World Wide Web was invented, we offered it to the world.
1.8 billion websites today run on the World Wide Web for almost 5 billion web users. The technologies and scientific advances behind high-energy physics, through developments in accelerators, detectors and computing, have historically contributed to the field of medical and biomedical technologies.
They also extend to a vast range of areas
such as aerospace, Industry 4.0, cultural heritage,
education,
outreach, human capital,
and open science. We are a powerful model for international cooperation,
taken as an example by other intergovernmental organizations and endeavors.
We work together for a common good and are a proven source of inspiration for future generations.
And a model for other international research projects. Did you know that €1 invested in CERN's research brings back 1.8 euros to society?
We have had and will continue to have an impact on all of our lives and on the world around us.
Understanding our universe means going further than outer space.
We are CERN, and we are going back to the origin of our universe.
Pushing science
and pushing technology.
Called quarks, an extremely strong force transmitted by so-called gluons holds the quarks together. The force between the quarks is so strong that it has never been possible to separate the quarks from each other. In ordinary matter, quarks can only exist in this prisoner state inside protons and neutrons. But where does all the matter come from? The history of the universe starts with the Big Bang, about 13.8 billion years ago. It produces all particles in the universe in less than a millionth of a second. For an instant, these particles form a hot and dense soup called the quark-gluon plasma, where quarks can roam freely. Scientists are keen to study the properties of this primordial state of matter, since it's crucial for our understanding of the birth of matter in the universe. At CERN, lead nuclei are traveling through a network of accelerators, where they go faster and faster, until they reach almost the speed of light inside the LHC. By colliding the nuclei, scientists recreate conditions that existed in the first instance of the universe. Inside a tiny fireball, thousands of newly created particles form a droplet of primordial matter, the quark-gluon plasma. But the fireball is extremely short-lived. As it rapidly expands and cools down, free quarks start to group. Protons, neutrons, and other particles emerge from the collision. The study of the production of these particles reveals the properties of the quark-gluon plasma. It is 30 times denser than an atomic nucleus, and even very energetic quarks are quickly absorbed. But for photons, which are insensitive to the strong interaction, the plasma is transparent. The plasma temperature is 200,000 times higher than in the core of the Sun, and it behaves like a perfect liquid without any internal friction. The study of the lead-ion collisions needs an enormous three-dimensional digital camera that surrounds the collision point. This is the ALICE detector. It records the direction and energy of particles emerging from a collision. By analyzing millions of collisions and comparing them with theoretical models, we can learn more about the properties of this primordial state of matter. The ALICE detector is installed in a cavern 56 meters below ground. It is 16 meters high, 16 meters wide, and 26 meters long. Its weight is 10,000 tons, more than the Eiffel Tower. The ALICE detector consists of several components for measuring charged and neutral particles. A huge magnet produces a field of 0.5 Tesla, forcing charged particles on a curved path. They leave signals in some of the millions of sensors in the tracking devices. Computers identify tracks by connecting these signals and determine the energy and type of each charged particle. The energy of electrons and photons is measured in so-called calorimeters, which are located further outside. Muons are similar to heavy electrons and are detected in the muon spectrometer. A large dipole magnet bends their tracks, and several detector layers record their position. The data from all collisions are recorded to mass storage, amounting to many thousands of terabytes every year. Hundreds of scientists from the ALICE collaboration analyzed these data. They are using the computer power of the LHC grid, which consists of several hundreds of thousands of computers distributed all over the world. The history of the ALICE collaboration starts in 1993, when the letter of intent is submitted to the LHC committee. The approval process takes almost 4 years and requires a number of detailed design reports. Since 1997, more than 1,600 scientists and engineers from more than 170 institutes in more than 40 countries have designed, built and operated the ALICE detector. Since the start of the LHC in 2010, ALICE has studied the quark-gluon plasma. It has measured the expansion and cooling process with unprecedented precision and observed how different particle types are produced and interact when they pass through the plasma. Over the next years, the ALICE detector will continue to take data and to extend its performance. Thousands of scientists from all over the world are looking forward to new discoveries about how the universe evolved from its first moments of existence.